for centuries, right? Physics has built this incredible picture of the universe, and a lot of it relies on symmetry. Perfect balance, laws that work the same everywhere. But what if? What if that's not the whole picture? What if some of the biggest mysteries out there, like why we even exist, why there's matter, are actually hinting at something else, something asymmetric? Welcome to the deep dive. Today, we are really getting into something that might just shake up that core idea. We've got this really fascinating paper here. It's from Philip Lilien, just out this year, 2024. The title is Asymmetry Noetherian Finsler Numbers.pdf. And our mission today is to unpack this, look at what it could mean, connect it to things we can actually see, or maybe could see, and make this pretty cutting-edge stuff make sense for you. We're talking about Asymmetry Noetherian Finsler Numbers, ANFNs for short, the core idea. Maybe asymmetry isn't a bug, it's a feature, a fundamental, measurable force. Okay, let's dig in. So first things first, what exactly are these ANFNs, like fundamentally?
Right, so ANFNs, they're essentially a new kind of math tool. Think of them as rulers, but rulers designed specifically to measure asymmetry in physical systems. You know how physics usually leans on symmetry, like things staying the same no matter how you look at them?
Yeah, conservation laws and all that.
Exactly. Well, ANFNs come from something called Finsler Metrics. And these are already a bit different because they inherently get this idea of directional dependence, like walking uphill versus downhill. It's different, right? Finsler geometry sort of captures that mathematically.
Okay.
ANFNs take that base and build on it. They give us a specific language for what the paper calls asymmetry-driven dynamics. Not just the symmetric stuff we're used to. It's like, imagine you had a black and white photo of the universe. ANFNs are trying to add the color, showing the parts driven by these imbalances. You get a richer picture.
A richer picture representing things like the matter-antimatter imbalance. That's huge. So why the need for new numbers? What problems are we trying to solve here that symmetry alone can't handle?
Well, that's the core question, isn't it? ANFNs aim to model a whole range of things where symmetry seems incomplete. Think about biology chirality. Left-handed and right-handed molecules like DNA. Why the preference? Or, that massive cosmological puzzle. Why is there so much more matter than antimatter? It's a glaring asymmetry. The paper also mentions things like asymmetric resonance operators, which are more technical but point to the same thing. But the big idea, the really profound part, isn't just saying, oh, asymmetry exists. It's proposing that asymmetry is an active, quantifiable force, maybe even the engine driving complexity.
Wow.
Yeah, it really echoes this line from the source. Breaking symmetry causes interdependence to emerge. It flips the script. Maybe the universe isn't just symmetric despite flaws. Maybe complexity arises because of those breaks in symmetry.
Okay.
So ANFNs could be the bridge, connecting the symmetry-based physics we know with these asymmetry-driven processes we observe, but maybe struggle to fully explain, giving us a more unified view.
All right, so if we're building a number system literally for asymmetry, how do you do that? Mathematically, it sounds like a pretty radical step.
It's maybe less radical and more an elegant extension. Like I said, Finsler geometry gives a starting point because it doesn't have that built-in assumption of perfect symmetry like, say, Euclidean space.
Right.
ANFNs basically take that inherent directionality and double down, weaving asymmetry right into the definition of the number itself. So conceptually, don't think of an ANFN as just one number. It's more like a package deal, a kind of two-part code.
Okay.
You can imagine it written like asymmetric stuff, asymmetric stuff. The first part holds the things we're used to and served quantities like mass, energy, stuff that balances out. But the second part, the asymmetric components, that's the real innovation. These capture the imbalances, directional weights, phase shifts, maybe how skewed something is.
Oh.
And it's the interaction between these two parts, the rules for how they combine, that defines this dynamical asymmetry. Even basic math, like adding or multiplying these ANFNs, has to be defined carefully to make sure this asymmetric character isn't lost.
So the math itself reflects the asymmetry.
Exactly. And the ambition goes further. The idea is that ANFNs could potentially generalize even more complex number systems like quaternions or octonions by baking asymmetry right into their fundamental rules. Like, imagine if I squared wasn't just mex1, but mex11 plus some tiny asymmetric term, or I wasn't just mexy, but mexy plus another small asymmetry, that kind of thing.
That's, the different way of thinking about numbers. Okay, so we have this abstract mathematical framework, but where does it actually connect with observable physics? What does this do to our understanding of forces and fields?
Right, the payoff. And this is where it gets really powerful, potentially. The paper shows how you can apply ANFNs directly to quantum fields to gauge fields.
So electromagnetism, the nuclear forces.
Precisely. Electromagnetism. the weak force, the strong force, and even cosmology, the universe on the largest scales. The key mechanism they propose is introducing something called an asymmetry tensor. Let's call it A.
Okay, a new tensor.
Yeah, and what this tensor does is it fundamentally changes our standard field equations. You know the field strength tensor, Fin, usually symmetric. Well, this theory proposes an extended version. Let's call it Fen F tilde. And this Fennies is the original Fin plus this new asymmetry tensor A multiplied by a small number that controls how strong the asymmetry effect is.
So Fin plus Avon. Got it.
Exactly. So Fin now contains the usual field information plus this new information about direction-dependent effects or maybe chirality effects. This means when you write down, say, Maxwell's equations for electromagnetism or the Yang-Mills equations for the other forces, but using this extended Fin.
The equations themselves now have asymmetry built into them.
That's it. They inherently include terms that describe directional effects. It's not just a minor correction. It suggests fields might behave fundamentally differently than we thought, especially under certain conditions.
Okay, here's where my mind starts spinning a bit. If the fundamental equations change, what does that mean physically? What are the really wild implications? What can this theory predict that maybe we haven't seen before?
Yeah, this is the exciting part. What does An, this asymmetry tensor, actually represent physically? Well, the paper throws out some intriguing ideas. One is that it might have a higher dimensional origin, maybe effects leaking from extra dimensions related to something called hypergravity coherence fields.
Whoa, okay, hypergravity.
Yeah, embedding higher dimensional physics into our familiar 4 dimensions through this tensor. Basically, encodes these subtle anisotropies, these asymmetries. It breaks perfect symmetry, but in a way that crucially still respects gauge invariance, a really important principle in physics.
Right, you can't just break everything.
Exactly. So observable consequences. We could potentially measure direction-dependent effects in fields, like the strength of a force might be slightly different depending on which way you're measuring. That's the prediction. It could show up as tiny changes in how particles scatter off each other in colliders or how they decay, things we measure very precisely. And cosmically, maybe we'd see weird patterns in large-scale magnetic fields or unexpected effects in how dark matter clumps together.
Okay, so what are the specific concrete predictions, like for electricity and magnetism?
For the electromagnetic field, the paper predicts we might see anisotropies, directionality, and how light or radio waves travel, especially in really extreme places. Think near black holes or maybe in regions dominated by this hypothetical hypergravity. It even suggests we might design lab experiments with really intense fields to try and spot these directional effects here on Earth.
Okay, and for the other forces, the strong force.
For Yang-Mills fields, the strong force stuff, it opens up looking for asymmetry-driven effects inside things like quark-gluon plasma, that super hot soup of particles.
Right.
Or maybe it affects how quarks are confined inside protons and neutrons. The prediction is for potentially new particle interaction signatures, totally new ways particles might interact because of this underlying asymmetry, things that could maybe show up at the LHC or future colliders.
New physics signals.
Potentially. And then, zooming out to cosmology, this framework could model asymmetries we already kind of see, like in cosmic magnetic fields or how galaxies cluster. And crucially, it offers a mechanism, a mathematical way, to potentially link that huge matter-antimatter imbalance directly to these asymmetry tensor effects. It could be a way to finally explain why there's more stuff than anti-stuff.
That is quite a possibility. So, wrapping this up, we've really journeyed from this bedrock idea of symmetry in physics to exploring a universe where asymmetry might be just as fundamental, maybe even more so. These ANFNs, they offer a mathematical language, a toolkit, to describe things that symmetry alone struggles with, like that matter-antimatter gap. It's a potential unifier. The big takeaway seems to be that the universe's beauty isn't just in its balance, but perhaps even more in its dynamic imbalances, its asymmetries.
Absolutely. And it's not just philosophy. This theory, as laid out, provides a framework and makes concrete, testable predictions. That's huge. It really invites you, the listener, to think about how deep this asymmetry might run. Is it everywhere? How does it shape everything? And it opens up brand new questions for experiments to chase. I think, given how incredibly successful symmetry has been for physics, the real test for ANFNs will be finding that experimental proof, seeing those subtle directional effects. That's when things will get really exciting.
So a final thought to leave you with. What if the very fabric of reality isn't just elegant in its symmetries, but actually far more complex, more dynamic because of its inherent asymmetries? And what new connections, what new kinds of interdependence really do emerge when those perfect symmetries break, showing us a universe even richer, even stranger than we ever imagined.